Welcome back to a course on multivariable calculus. In this lecture, we are about to see the applications of integrals. First of all, let us start with the applications of double integrals. Here you may very well see the first applications that is given as density and mass. In an integration of one variable, that is when we are about to integrate only one times. Okay, there we have an application of integral in density and mass, that is the moments and the center of a mass can be calculated for a thin plate or lamina with constant density. A lamina with constant density, the moment and the center of a thin plate or lamina with constant density can be calculated using the integration idea. Since we are extending our ideologies to a two-dimensional case, we consider a varying density. Okay, if the density is fixed, then we have calculated what is with the help of single integral. Since density is varying, that is a variable density is considered, so the density shall be expressed like this. Okay, and using some physical ideas and mathematical calculations, we see that the mass is the double integral over the given region of the density. If your density is a varying quantity, just integrate over the given region to get mass quantity. So the same ideology can be extended to calculate the electric charge. Okay, if you are given your sigma of x comma y, then your electric charge q can be calculated using this. As I told you in the class, we are not going to deal much about applications of double integral, but applications of triple integral is included in our syllabus. So let us see how it is happening in double integral, and let us extend our idea to triple integrals. Here you may very well see that a charge is distributed over a triangular region which is given in this figure. So in this figure you may very well see that your x ranges from 0 to 1. Okay, and your y ranges from 1 minus x to 1. So your integral is this one, and your sigma of xy is given to be xy. So do the integration, and this is your total charge. Now we are extending this idea to moments and center of mass. Center of mass. If it is a one-dimensional thing, your center of mass is a single point. If it is a two-dimensional thing, then your center of mass is going to consist of two coordinates, namely x and y. So the center of mass at x is given by double integral over d y multiplied with density. Okay, about y-axis means instead of y you are going to have x, only this thing. So this is the difference, and with which you can calculate the moment. Moment is generally mx my. So this is the coordinates for moment. Similarly, you can calculate for excuse me, mass as well. So mass, the coordinates x bar y bar is moment upon the mass quantity. Okay, you know to calculate mass, that is double integral over the given region to density. So you just do those calculations. Here you are asked to find out the mass and center of mass of a triangular lamina with vertices. We just plot these vertices and see what is this. We have 2 points. Okay, so if we have 2 points, we can very well find the equation of the straight line joining these 2 points using the formula y1 minus y2 upon y minus y1 upon y2 minus y1 equals x minus x1 upon x2 minus x1. Substitute the given points in 1 0 and 0 2 into it, and you may very well see your y is 2 minus 2x. Okay, here also we may very well see that x ranges from 0 to 1 and y ranges from 0 to 2 minus 2x. Integrate over it, you get your mass quantity. Then your x coordinate is, you just multiply x with the density and integrate over the same region and divide by your mass. You are going to get the center of mass, that is your x coordinate. And similarly you can calculate for y coordinate, and these are similar problems that we can that you can go through easily. Sometimes we may be in a need to convert it to a polar coordinates and do the integration. So whatever the things that we have studied in double integrals shall be applied in calculating these things, right? Let us now pay our attention to applications of triple integrals. Initially, we will start with the applications of triple integral to find the volume of solid. So, just like we have calculated the surface integral with the help of a double integral, yes, using double integrals, we were able to calculate the surface area as well as the volume. So, as we have calculated the surface area using the double integral, we are able to calculate the volume using triple integrals. How are we going to do it? So just triple integral over the over the solid E and then dV. So this dV is appropriate when we deal with rectangular coordinates. It has to be replaced with dz, dy and dax are the things if we have to do any conversions that we can do. Okay, here we are asked to find out the volume of a tetrahedron bounded by the three planes, that is x plus 2y plus z is equal to 2 and x is equal to 2y and x is equal to 0 and z is equal to 0. So here we'll have to mark all these four planes and you may very well see this is happening. Okay, so from this now we'll have to project this onto D and see what is your region D. So it is some triangular region like this. Okay, now first let us see how Z is varying here. So your Z is varying from 0 to, from this you can reduce your Z to be 2 minus x minus 2y. So your Z is varying from 0 to this quantity. Fine, and you have projected this onto xy plane and see you are getting this one. So from 0 to this line you will have to identify, and this line also you will have to identify. This is the line that is got from projecting this onto xy plane. So from this, if you make your z to be 0, you are going to get x plus 2y is equal to 2. From this, your y is 2 minus x upon 2, which is 1 minus x upon 2. Okay, you have got your y varying from x upon 2 to 1 minus x upon 2. If you plug these and your x of course varies from 0 to 1, if you plug all these informations into the integral, you may very well see that your integration becomes like this, and do the integration and evaluate the value. That's it. We extend the ideas that we have studied for double integrals to triple integrals. This is the thing that we were doing. So similarly, instead of taking a two-dimensional domain, if you take a three-dimensional solid, you can very well see that the mass, the density of any solid is represented as a function of three variable, and the mass is calculated by just by integrating your density over the solid, right? Similarly, the moments can be calculated, moments in coordinate planes in yz plane can be calculated using triple integral x times of density, and in xz plane as y times of density, and xy plane as z times of density, and the center of mass in all the coordinate planes is given like this, and the moments of inertia can be calculated using these formulas. Okay, once you have all these things, you can directly do the integration and see what is happening. Here also the main thing is okay, let me explain the problem. We are asked to find the center of a mass of a solid of a constant density. So here it is very well given that our rho of xyz is some constant. We Okay, let us take that as rho, that is bounded by the parabolic cylinder x is equal to y square. So x is equal to y square. If you plot that in a two-dimensional thing, you can see very well see a parabola like this, and the planes x is equal to z, z is equal to 0, and x is equal to 1. When you do all these things, x is equal to one line, you just have a plane, right? And z is equal to 0, you have a plane, and x is equal to z, that also you are going to have a plane. So the intersection of all these things will give you the solid. So here you may very well see that your y quantity ranges from -1 to 1, and your x quantity, so from this your x quantity ranges from y square to 1, and z ranges from 0 to x. So when you plug so from this you may very well see that first you can integrate with respect to z, and then come to x, and finally with respect to y. So when you find all these things, you just do the integration, find the mass. Once you find the mass, then find the center of mass, and finally we are asked to find out the center of mass. Yes, once we find all these things, we can plug here. Okay, note that center of mass of a solid of a constant density. So in all these things we have this rho that is coming, and this is the moments of inertia, and finally we'll have to divide this by mass so that we'll get the center of mass. Once we do so, we get this one. Thank you.